The topic here is the illustration of design process. So normally design processes are whenever you undertake a design process, you have to keep certain you have to follow certain rules. Okay, and those rules are something like designed by uh, some hierarchy, right? So what is the hierarchy that needs to be defined whenever you want to go with the structural design is our first topic. Okay, so this is hierarchy of structural design. The first point is whenever you begin a process, right, you are supposed to do this always top to down approach, right? So that will be the first thing. Process, in a sense, the design process is top down approach. The outermost, the biggest block will be decided first, like, okay, what you want to design. I want to design an amplifier. That's the topmost layer. Then what comes inside an amplifier, what blocks will come, that is one layer below that. So top to down approach is like this. Okay, so in a top down approach, always you try to dictate the complex function first, and you further divide that into a lesser complex sub functions. Okay, then which can be further subdivided into more simpler sub sections, right? This whole process will continue until you reach the lowest level or the easiest or the most basic functions like and or gates or something. Until you reach very simple functions, this process needs to be repeated. This is the design approach, or this is the second step in the hierarchy, right? So the top down approach dictates you what, right? Dictates complex function, any complex function, right, has to be divided. You have to divide that into less complex sub functions, right? Which means this the complexity of your sub function is slightly lesser than the original function, but this is still complex. What you can do, you can further subdivide, comma, I'll write which can be further subdivided to more simpler subfunctions, right? So this whole process should be right carried out further until you reach the what you call basic functions. Basic function refers to some simple addition operations, subtraction, multiplication, or maybe and or not gates, something like that. Okay, that's this thing. Then the third point in the hierarchy is that with the increase in the complexity, the system's organization will change as different factors relevant to the creation, right, of that particular level. All right. So with increase in complexity, the organization of the system changes as different factors evolve. In a sense, there are different factors on which your system's design, right, depends upon. As they evolve, you have to change the organization of your system. In the sense, which blocks comes where, right? You may have to modify. I may put a battery on the leftmost corner initially, but later on I need to move it to the right side because, right, of some heat dissipation issues. Maybe. Okay. So this is what is the meaning. All right. Then the fourth point is whenever you put your components onto the layout, you should ensure that the components interacting more frequently should be physically close. Okay, otherwise you need a longer interconnects, longer wires cause more problems associated with the magnetic fields, the currents, the resistance, and high bandwidth, etc. Right? So that will actually cause more problems. So the hierarchy says that layout should ensure that the components interacting more frequently should be physically close. Okay. Why? It's obvious because when you don't do this, right, you need more longer wires, longer interconnects, which results in more resistance, more magnetic field, and these wires will affect the working of the other components as well. Okay, just to avoid that, you have to follow this. Then the design hierarchy should be aimed at minimum interaction between the subparts, right? Because you want to have an independent design, right? When I make a connection from one part to other part, it should not affect any other subparts present in the whole circuit. Okay, so that's the next point in the design hierarchy. Okay, that is the design should be aimed at minimum interaction between subparts, right, to achieve inde- independence of design. Design should be independent. Every component has its freedom to work this thing. So the idea is that you identify how much coupling is there between right every component, and you can try to eliminate that easily. Okay, so that's how you do actual part of the design process. Then functioning of the system should have maximum concurrency, wherein most of the right gate on the chip should work most of the time. In the sense, there should be a concurrency in the working. Design should be taken care of that concurrently every part of your circuit should be or should be capable of working simultaneously, right? So that's the next point, the functioning of the system should have maximum concurrency, and the whole process should be able to adapt to the new technologies in a very short time, right? You design the whole system using the current technique, maybe, okay, current technology, but we know that technology is changing very quickly. So if I want to update the current design to a new technology, I should be able to do that, right, using a process such a way that you adapt to the new system, right, in a very short amount of time. Okay, so that means your design process should be technology independent, right? So it should not depend on any of the particular technology. That's the next point in the hierarchy. Okay, so the processes should be able to adapt to the newer technologies. Or we can write simply new technologies in short time. All right, these are the points of the hierarchy. Now let's move on to the next topic, that is the general arrangement of a 4-bit arithmetic processor. Okay, now in order to understand how do you arrange the components of a processor which is capable of performing a 4-bit arithmetic, right? You should be having see, first is that you give some data. 4-bit arithmetic in the sense I take two 4-bit numbers and I perform arithmetics. So this suggests that you should be having a facility to store your numbers. It means I need memory. That's the first thing. Okay. And how the data goes into the memory, there has to be an input device. And how do you get your result out of this processor? There has to be an output. So input, output and memory, they're required now. So in addition to that, in order to perform the arithmetics, we have a specific unit called ALU, arithmetic logic unit. So whenever you do the arithmetics, it is required by the processor that there may be a something like a uh, temporary partial results. So in order to store them, the device requires a specific type of memory called registers. And in order to control the whole process, you need a control unit. Okay, so these are the basic uh, components which we require, right? So we first write them, then we'll discuss further. Okay, right. The fundamental blocks required and their interconnection are, are shown below. Now we'll draw a block diagram showing that what are the different components required. Okay, the first block is, this is a control block, or I can call it as a control unit. Then the second block, this block is the ALU and registers, followed by the third block. This is the memory, and we go for a fourth block. This is, it's I/O, indicating that input or the output. Okay, now so these are the four blocks. As I understand now, I what is my target? I need to build a 4-bit processor which is capable of doing arithmetic. So I have to give the data, so I need this I input. When you give a data, where it goes? It goes to the memory. So there is a memory requirement, and my processor should have a memory. Okay, I give two numbers I want to add, right? So I instruct the machine saying that, okay, take the two numbers and add. Two numbers will be, both the numbers will be stored in the memory, and ALU will read the data one by one, like 4 plus 8 I want to add. So both the numbers will come into ALU. So there is a register, right? Register bank normally called as. So registers are temporary storage. Okay, so it is associated with the ALU itself, because temporary storage of data happens whenever you multiply bigger numbers. See, right, like 25 into 35, you see that there is a partial result coming, 5 into 25, then 3 into 25, etc., right? So to hold them, you need registers. So ALU and registers are associated, and they are inside the same block. Now see, there is addition, multiplication, division, subtraction happening, right, in a different fashion. So to control them, we need a another block that is called as a control unit. So you are fine with all the four blocks, why we have written them here. Now they are connected, right? They have to be connected. There has to be an interconnection, right? So the interconnection happens in the following fashion, in the form of wires. All right. So and those wires we call by different names. Okay. So the first wire is called as, let me write that. So the first set of wires that we are writing here is, okay, let me write like this. So this is the first set of wire, Fine. And we have three types of wires. Okay, all together. First one I use a different color now. So the second wire that I am going to use now, this has a different functionality compared to the first one. Okay, so we change the color. And there is a third type of wires connecting the whole system, and I'll draw it say here below. Hmm? All right, so okay, now, so the first, the blue colored wires, we are going to call it as the control bus. Okay, and next, the red colored one, we will call it as an address bus. And the last one, that is in green color, we'll call it as a data bus. All right, now, why do you need three different types of wires, right? Basically, they are simply wires, right? So, uh, if you remember, the basic computer architecture uses every number being stored in the computer in the form of binary, correct? Binary numbers. So if you say I have 8-bit memory, means I can store 8 bits in a single space, correct? Yeah. Maybe 11110000 is my number, correct? So whenever you want to store that 11110000, I have I have a requirement of 8 locations. Okay. Now, when you say you are reading 8 location, how many wires do you need? You need 8 wires, correct? Because every location has to be read by one wire. One first wire will carry one, second, third, and fourth will carry 1111. Then remaining 4 wires will carry 0000. So 8 wires. Okay. So these 8 wires all together you call as data bus because you are reading the data. Are you okay? What is data bus? Fine. Now, let's move further to the address bus. Okay. Address bus is something like, consider your whole memory system like a residential area, a cluster of residential plots, right? Where, let's say, I'm managing a delivery company, and I have to deliver a packet to one of the house, right? So maybe take that in a computer system, this same thing has to be is analogous to the writing of a data. I have some data, my computer has data, ALU has a data. This data needs to be stored in a specific location in my computer. Okay, computer memory. So how do you do that? What I do, I see what address, and I go and I deliver the packet. Same thing should happen here, right? There has to be a space for writing down the address of the memory, right? You cannot write the address on the data bus, correct? Because data bus is already carrying the 8 bits of data. Some others, it has to be some, there has to be some other space, like, so I have a courier. The courier cannot contain the address, courier's envelope will contain the address, correct? There is a difference. Same thing. So the address of the location where you want to write, or it can be the other way, you have to go and pick up a deliver pick up something from a location, right? You need the address, right? So to read or write the memory, you need an address. So where do you write it has to be, right, passed through different set of lines called address bus. Okay, so requirement of address bus is also fine now, right? Then see, whether you are going to perform a read operation, write operation, or any other operation supported by the computer architecture, needs to be passed through a separate set of separate set of lines called as control bus, right? Which operation to be performed at what time, who will decide? Control unit will decide, and it passes the message to all the other units connected through the control bus. All right. Okay. Now let's see how the connections are made. So the connections are like this. So I'll use the, sorry, just a second. Okay, the connections are going to be in the following fashion. So from the control unit, you have to have a connection with the address bus because you always tell what address. Okay. And the control signals should be passed. All right. Now there is a connection. The data has to be read by the ALU. So that's why the control will be issued. So the arrow mark is downwards. All right. And you see that the data will be read by the control unit. That's why it is this way. Right. Then you have two directional connection between these two, because whenever you send the data and you might have to receive the data for AL, right? And the memory unit will definitely take down the address. So the memory unit has to read what address it is, right? So address will be read by the memory, and always it has to be bidirectional. Data can come to the memory or data can go out of memory, right? So you can see that there can be a command issued to the IO device saying that yes, now you read the data, now give the data, or now you read the data. That's why. Okay. At the same time, the address can be issued from this particular location. You read the data. You give me the data from this location of this, or you may have to read or write. Okay, then the connection of the data bus, it should be bidirectional, correct? Because you may have to send some data to the IO, or you may have to read the data from IO. All right. So the basic architecture is like this. For any given general 4-bit arithmetic processor, we need the following components. Okay, I think you can explain this by yourself, right? So this whole diagram you can explain by yourself, right? Now, in this first, we'll take up the concept of designing of the data path, because see, you saw the data bus and its a requirement. Our first intention here is to consider the design of the data path. Okay, so to design the data path. So data path is something through which the data can be passed, right, among the units of your uh, computer or the processor. Okay, now data has to be, right, data has to flow, right. For any system, for any block which you consider here, data will come in from one side. There is a control unit which sends control signals to that, and after the control, it performs some operations on your data and it will go out. Okay, we have two options here. So in order to design this system, specifically the data path, we need to consider one of the following technique. Okay, interconnection strategy. So to design this data path, select the interconnection strategy first. Right, we need to do the selection. What do you mean by the selection of this? It's like this. So we have, let us say this is the block which performs one of the block. It can be control, it can be ALU, it can be memory, it can be IO, input output. Right. In any of this, our intention is we will send the data in from one side. Okay, this is the path in which data enters. And after performing some operation, the data will go out. This is one option. And at the same time, you may require, that's not this, it's the reverse. The arrow mark should go inside. So I'll draw this way. Right. So here on the left side, you have data input. Here you have the data going out. That's output, right? And you provide some control if required. Now the data path is this, right? You should be, during this, whenever data comes in and some control is provided to you, you should be capable of performing the basic arithmetics. First thing, then logical operations. Then you need to perform the shifting operations, right? Then you also need, as I mentioned earlier, you have to perform the temporary storage of operands. This is one option. Okay, data will be provided from one side. You do these operations along the data path according to the control issued, and once you have the result, provide the output. Right. Either you choose this, because you see our point, the point mentioned here says that select the interconnection strategy. How do you do the interconnection of this? This is the first option, or I'll write a or here, because either you choose this or the next one among them you need to choose. All right, so the second option is, this is something like the IO part of that. In an IO device, right, you have to apply this particular technique only. There is no other option available. So this is something like the data will come and go from the same side. I don't have a separate option to give the data out. So you see here, this is the data input or the output. Okay, data will come from this side. I have the control signals being issued. Okay, this is the control signal, and once again I have the data path as shown here. This has the similar structures, the basic arithmetic. You have to perform the logical operations. You need the shifting operations, and you need to have a temporary storage. Right. So choose which one you want, either the first one or the second one according to this. Once you choose this, right? Once you choose all of them according to your requirement, in the sense, I come back and I check. I have shown here that, okay, these are my 4 units and I need to make the connections accordingly. So what you do, first you connect everything only by using the, for each of the block, connect the data bus only, in the sense only the this line I connect for every block. And also I will connect what, I will connect the control signal. So you see, this is our idea now. Either you choose the first option or the second option, because data will come from one side, goes to other side, and there will be a control as an input if required. So use this and make the connections of all the subunits. Right. So choose this first. So choose one of them, whatever is the interconnection strategy you want, you select, right? Now, once this is selected, you have to make the connections as per your requirement. Okay, uh, the the data path has to be applied to each subunit of the design as per the requirement, as per the requirement, and whatever you have chosen earlier. Okay, as per the requirement and the interconnection chosen, whichever interconnection you have chosen in the previous step, and considering the requirement of your design, you have to connect the four different blocks: input, output, registers, ALU, and all operations. Any operations you want to perform, that needs to be clubbed together to perform the interconnection. All right. Now, how this has to be done, right? We have to write another block diagram to understand that. That will come. That will be the next step of the design. Okay, and we will see that in the next class.